I'm Jonathan Bishop, and here's my lab report for Lab 5. In the lab for the models, I used the force of gravity vector, which is 9.8 times the mass of the object in the downward direction, which is the negative. And then I have the force of drag, which you would add to this gravity vector for the net force vector, and that's going to be the object's velocity times a constant b in a negative direction, because you want to subtract that from the force of gravity, so you essentially get these negatives right here to cancel out because it's going to be in the opposite direction. Okay, so what I did is I dropped a stress ball and compared that with a plastic bag. And here's the video. You can see the stress ball falls faster because there's not a big drag force on it, while the plastic bag, which has a big drag force, falls slowly and at a constant rate. Okay. Actually, let's go back. So the time step for this was 0.021, starting at 0 seconds, and then the end time was 0.542, which is what I did here, 0.542 seconds total with a time step of 0.021 about. And then here's the force of gravity vector right here. And then here's my constant b, which is a negative 0.032, which is incorrect, and I'll tell you why that is later. But here's my model. And I graph the points of these. What I like to point out to make this graph, basically it's iteration. Ball velocity is equal to ball velocity plus the net force times time step divided by the ball's mass. That'll give you the ball's velocity, which you can predict for the next ball position, and then you keep doing that until you reach 0.54 seconds. So I graphed these results. Actual data is these blue diamonds, model data is these green triangles, and the model data is right here. The reason why my actual data is lower, it's not supposed to be, it should at least be higher than the model data, because the model data is the exact data, more accurate data, is because of the angle of my camera or the distortion from a fisheye, which is an error. Which is why my constant b had to be a negative 0.3032, which is impossible. But here are my results, and my actual data comes fairly close to predicting the actual data. My model data, yeah, actual data. So I did the same thing for the plastic bag. You can see here without drag, no terminal velocity is reached. But with drag, a terminal velocity is reached. You can't see it well here, but there's an actual small curvature here, and then it goes straight into a line. And you can see that from my model data and actual data. And my model data actually is fairly accurate with the actual data. So a terminal velocity is reached because the force of drag eventually compensates for the force of gravity canceling each other out, making the net force 0, which actually answers the what if question. What does it mean question. The what if question is what if the object started with an initial velocity. So I graphed that also. If it had an initial velocity and still had drag, you could see it still reaches a terminal velocity. Without drag, it just falls at a faster rate. Thank you.